Does anybody realize right now how short 48 hours really is?
Yes.
Are y'all surprised how fast the time passed? It was amazing. Not 48 hours ago, we were standing here opening this whole event. Y'all didn't know each other as well as you do now. You had a lot more sleep. There's not nearly as many yawns out in the audience as I see right now. I got to tell you, y'all have been amazing. Welcome to the final presentation of Aggies Invent. We are live streaming this. I've got a YouTube channel up, and their YouTube link is over there if you want to send it on to any of your friends. We tweeted out the YouTube channel, so you have an opportunity for people to join it. It will stay up there, so you'll get a chance to see your presentations as well. We had over 60 students involved. We had 10 different teams form out of that. 19 need statements. 9 need statements actually didn't get worked on, but 10 need statements did. We had 11 organizations and mentors associated with us, and the mentors that we had were amazing. I'll give a little brief on each one of them, but they were truly amazing. 2 graduate student mentors. Where are my 2 graduate student mentors? They're back there. There's one of them. Where's the other one? I don't know where they are. But let's give them a hand. I mean, they did a great job. And then finally, I really want to thank Jim Wilson, who's standing in the background over there, but Jim's always in the background. And Jim's entire staff, some of whom did not get sleep from 9 o'clock yesterday morning until about noon today. So pretty amazing. So his staff has really taken care of a lot of things. So it's been outstanding. The dance, the design, the deal, the doing, and now the deal. I told you all about those concepts in the very beginning. Now you've lived them. Now you know what I'm talking about. Unbelievable mentors. From Dr. Chomatoff to Dr. Joe Kerwin. Dr. Joe Kerwin's here someplace again. I saw him here. Thank you so much. And Greg's right over here. Dr. Bob Skelton, he was not here right now. Kylie Wren. Dr. George James, he's up here. Thank you so much. And Dave, I know you're back someplace. There's Dave. Outstanding mentors. We've had a class of mentors here that y'all have had access to that has just been unbelievable. 2 of our mentors, Dan Jackson and Dr. Jason Held, were also available to us. They were available to us by remote. And Ben back there. Ben's been amazing throughout the entire weekend. So Ben, thank you again for everybody that's been involved. This is outstanding. This presentation is up on your shared drive, so y'all can download it. That way you can at least remember who you've been able to interact with throughout this entire weekend. Truly legends in their field. Here's the dance. You started out getting going. You started talking to your mentors. You started finding out about need statements. You started forming your teams. There was this dance going on. It was speed dating. You had a great time. We fed you pizza. You found out what was going on. Then the design. This is where the hard work started. This is where you started to understand a little bit more about what was going on. You were starting your design process. We told you, and you gave us 3 or 4 different designs, and then you had it down selected. Then you started building. I'm really excited about some of the builds that y'all have. Building, just so that you know, we had over 150 3D print jobs printed this weekend. That represents almost 500 individual parts. So we printed the heck out of things this whole weekend. Y'all did a great job of coming up with designs. You did a lot of testing. We saw some failures. We saw some great successes. So outstanding on that piece of it. We watched a little bit of Aggie football. We streamed it. Whoop, and we won. Whoop. However, deadlines loomed, and the interest in the game waned really quickly. The entire place cleared out here in about 10 minutes. We watched the opening drive. The Aggies didn't do so great in their opening drive, and everybody kind of goes, I got to work on my presentation. So they left. Sleep was optional. All right. So found some people sleeping on chairs under the 3D printers. I wanted to make sure they kept the jobs going. Found some people sleeping on couches, you know, wherever. But sleep was optional throughout this entire weekend. Now's the deal. Now it's time for you all to sell it. We've got an outstanding section of judges here, and I think you're going to enjoy judges. I think you're going to enjoy seeing what we've got. You got 10 minutes for your presentation. Everyone take a look around. Turn around. See that timer back there? It's going to start when you start. When it goes 0, I'm pulling you off the stage. The reason is because it's not fair for everybody else. The judges will have 5 minutes to ask questions, and they'll be scoring you throughout the entire time. After we get finished, the judges and I are going to go into a room. We'll do some decisions, and then we'll choose first, second, and third place team. Our judges are Ken Bowersox here on the left. He's a former astronaut and a space consultant. Mr. Andrew Rush is right here. He's the CEO of Made in Spacey. And we really spent a lot of time working together with these need statements, so we appreciate all of the area and the time that we've worked with. James Benham's over here. James is CEO of JB Knowledge and also Binary Space. This is a maker space in downtown Bryan that if y'all have access and things like that, it's a maker space in downtown Bryan. Dr. Dimitri Lagudis, who is right here, and Senior Associate Dean for Research for College of Engineering, and Dr. George James is right here. And some of y'all were able to have the opportunity to meet with Dr. James. Outstanding set of judges. Couldn't be more pleased with the people that we've got involved. All right, it's showtime. First team up is Team Clean Sweep. So y'all come on up here and get started with it.
Serious problem on the International Space Station is foreign object debris. Particulates such as hair and skin, food crumbs, and chips or fibers off of everyday objects can make their way into the station systems or an astronaut's eye.
My left eye slammed shut in great pain, and I couldn't figure out why my eye wasn't working. I was thinking, what do I do next? I thought, well, maybe that's why we have two eyes, so I kept working. But unfortunately, without gravity, tears don't fall. And so you just get a bigger and bigger ball of whatever that is mixed with your tears on your eye until eventually the ball becomes so big that the surface tension takes it across the bridge of your nose like a tiny little waterfall and goes goosh into your other eye. And now I was completely blind.
This device uses common adhesive materials such as duct tape to catch the debris that passes through the outer case, which then gets trapped by the sticky core. The Clean Sweep is also strong enough to withstand wall impacts of 5 feet per second or more without breaking or fracturing. You can stick it to the wall or let it float around to catch debris passively. In addition, you can physically grab it and sweep it through the mess for a quick cleanup.
So we are Team Clean Sweep, and as the astronaut you saw in the video, Chris Hadfield said, there is no situation that you can't make worse, and this is especially true in space. If, particular debris is floating around, it can get into sensitive systems, it can get into experiments, it can get into your eyes or lungs, it can be a big problem. And if there were a massive disaster, like something were to impact the space station, or if something were to break catastrophically, then this is going to make the situation much worse with all this debris around. So we wanted something that could help clean up these kinds of debris and make the station a safer place and a cleaner place for the astronauts.
So we broke down our needs statement into a list of needs and constraints and saw that we needed to create a device that was small, unobtrusive, and lightweight. It should be able to move passively and freely throughout the ISS without using any electronics or propulsion. It should also have an adhesive material that's easy to insert and renew. And it should also be able to withstand wall impacts and collisions moving at a speed of about 5 feet per second. Then we, based on these needs and constraints, we made a list of engineering specifications and got a list of numerical targets that we strictly followed throughout the design process. We also analyzed a functional block diagram to make sure we were always on the right track. And as you can see from our inputs, functions, and outputs, the list of inputs is simple, like duct tape. It's cost efficient. And just from a small list of inputs, we get complex, maximized, and optimized outputs. This goes to show that our product is very efficient. Before we arrived at our final design, we had a couple of alternative ideas. We first thought of the structure of a soccer ball, and we saw that this would provide a strong shielding structure as well as be able to roll and move freely throughout the ISS. However, this wouldn't fit within the restrictions provided by 3D printing. We also thought about analyzing swallow birds, and we thought about how they use their beaks to capture insects and bugs while flying through the air. So we wanted to implement an inverted sticky structure that would maximize the surface area and easily trap particles. However, this would require some sort of propulsion, so we discarded this idea as well. Nonetheless, we combined the advantages from the previous two ideas into our final design that was based on the structure of a die. So we made sure it was structurally sound, it could roll and move around freely, and we also used an inverted sticky structure to maximize the surface area to capture particles. We did some mathematical analysis using basic kinematic equations and the velocity given to us to find the pressure that would be exerted during a collision on our structure. We found that this pressure was such a small number. It was 10 to the power 5 times lesser, 10 to the power 5 times smaller than the actual yield strength of our material, which only goes to show that within a wide safety range, our structure is strong and structurally sound. We also analyzed the surface area of different designs. We found that our structure would be the best because it would provide 1.8 times larger surface area than that of a cylinder, and all the spheres would provide a slightly larger surface area. It would be a lot harder to wrap the tape actually around the spheres, so we found that given the simplicity of the structure, this would be the most optimum design.
So with our final design, as you can see, it's evolved over the weekend. It consists of 4 parts. Our base, which has an X-shaped middle with railings to hold in place our core. The cap, which has it has indentations for the male ends at the end of the columns so it can secure itself using friction, and 2 plates which slide together in order to form the core, which is then wrapped around duct tape, and it will just slide in and rest on the railings. There you can see zoom in on the indentations in order to hold it together. We added more ball-shaped recesses in order to help it lock into place and make sure it doesn't come apart while it crashes into a wall.
This represents our available printing space. You can see that we were able to fit our print into the required area. If we ever want to adopt a larger design, we would add meshes around the outside to make it less likely for outside objects to stick in and get stuck on the tape.
As mentioned previously, we definitely have evolved from, popsicle stick design to a really nice 3D printed model. And so our end product really met the size requirements as well as the weight of it, which is only 35 grams opposed to the 100 gram limit. And in addition, we were able to further implement this with a dual tape application. So when it's passive and floating around the ISS, there are tapes on each end of this cross section, kind of like a filter. But if there is ever a case where there's a spill, an astronaut can easily tape it to this inverted and wrap it around in less than 30 seconds to sweep up all the mess if an accident occurs. And so we've tested it. It's very structurally sturdy. It's small, doesn't get in the way, and it's really neat design. So for some alternative implementations, we can use this as a portable storage device. So it's floating around and you happen to have a pen, you can kind of store pens in there, float around you. We can use this for recreation purposes as well, putting LED lights or even using this as a dice to play games. And lastly, we heard from a few astronauts that it may get a little smelly inside, so you can actually open the cartridge and maybe put an air filter there too. So there's many implementations for this.
Some feature improvements that we have, we can add some photoluminescent materials to it to light up the way when it's dark on the ISS. We can also add some LEDs to it to determine, hey, when do you need to change the adhesive materials? We could also add some sensors if we are allowed to use some circuitry, to detect, toxic air levels within the ISS. We can also add some self-propulsion so that we can be completely autonomous. It can just, cruise around the space station and clean up areas that, it needs to clean up. Then also we can incorporate a system where, they have the tape inside of the system itself. So instead of astronauts going about trying to find, materials to put onto our clean sweep, it's actually in there and you can dispense it and then apply it to it as well. And so the main problem, on the ISS, or a big problem that Chris Hadfield was talking about, was the, debris on the ISS. And, these debris, get into an astronaut's eye, hinders them from doing his job, and also these foreign objects can get into different electronics and potentially, harm them and damage them. But we decided to create the solution, called Clean Sweep. And the way it works is that you apply the adhesive on the inside and also the outside if you choose to. And then foreign objects will come and attach itself to the Clean Sweep, and then it stays on, it doesn't come off. So you can pass that around if you want. So it's a very simple system, and we used it to, or we developed it to be, 3D printed on the ISS. So instead of, sending these up by space station, which is both costly and not efficient, we can send up our plans, be, manufactured on site and assembled, and it just makes it a lot more efficient and a lot easier for the astronauts. And this system also has a high potential to be something greater, and that is why we decided to develop the Clean Sweep.
Thank you.
Different. Had this been done for a gravity environment?
If we were to make it for Earth, we would have to figure out a way to defy the gravity, so we would need some sort of propellers. And I think in that case, we could use something based off the swallowbird design, with actually like an electronic system that would let it allow it to propel and go through like at different altitudes to go up and down, since it can't easily float.
Was your size given by the limitations of the printed capability, or did you have another size that you felt like would have been optimal?
Yes, we were given a restriction of 10 centimeters by 10 centimeters by 14 centimeters, which is represented by this box. We originally thought to make it a 6 centimeter cube, but we thought we would just push the limit since we still had a lot of space left over. We decided to go with 7 centimeters, and just to further increase the size.
And as you can see, we efficiently printed this in pieces, and so each of these pieces fit this box properly.
So back to the needs statement. What are they doing right now?
As of now, they have normal filters, but they said that those filters are not able to capture all of it. Like there's still smaller particles that do not go through the filters. And that's why they wanted something additional to pick up, like a secondary mechanism to pick up whatever is left out by the main filters.
And it takes a long time for the debris in the air to slowly make its way to the filter as things flow through. So the system would be like, oh no, you were eating and made a small mess or something. You grab your clean sweep off the wall, sweep it up, put it back on.
So let's talk about duct tape. What type of duct tape do they have?
They have two kinds of duct tape. They have the duct tape, like that we use, the silver duct tape. They also have Kapton tape that they can also use in the system with fit both.
You tested it with both?
We don't actually have any Kapton tape here, but we know its dimensions and we know it'll stick on it.
So we wanted to just use materials that are readily available on the ISS to make it easier for the astronauts to use. And they don't have to ship up special adhesives just for the product.
All right. Thank y'all very much. Appreciate it.
famous Jedi once said, "Do or do not, there is no try." Every year, billions of dollars are spent on space research. Data for this research is collected through the use of several large satellites. Enter the CubeSat. CubeSat is a picosatellite that simplifies satellite design immensely and is contained within a 1-liter volume cube. Today, the ISS has 3D printing capabilities, providing opportunities for a revolution in CubeSat manufacturing. Now, instead of a CubeSat being assembled and launched in one piece, we can 3D print the frame and assemble it on the ISS. Welcome aboard Cube Station. Cheaper and lighter. Cube Station, the universe in our hands.
Howdy.
Howdy.
I'm Mark Wager.
I'm Nathan Glazer.
I'm Andy Castrua.
I'm Siva Praneeth. I'm Ronak Mohanty.
And we are Cube Station, CSAT for short. What is the CubeSat standard? Well, CubeSat is an economical and portable picosatellite that is roughly 10 centimeters cubed. What it's used for is mostly for collecting scientific data in and around Earth's atmosphere. Applications include natural resource management, at large-scale asset management, and then also crop resource management. Normally, a CubeSat is created with either aluminum or steel parts and shipped up via rocket up to the ISS and launched from there. However, we plan to use a 3D printer on board the ISS and print it with ABS plastic. Now, you may ask, why CubeSat? Why not just a regular satellite? Well, CubeSat is significantly cost-effective compared to these large satellites, and also it's very modular in design, allowing for easy shipment and very easy redesign.
Okay, so over the past 48 hours, our main objective was to design and develop a telescope support structure that can be 3D printed in space. And we were given this project statement with a set of constraints. Part of these constraints contributed to size considerations, as well as consideration to putting solar panels onto the outside, and for the final structure being able to withstand a deploying force of 45 newtons. And we also wanted the entire structure to be easy to assemble and to contain as few parts as possible. And what sets us apart is our stretch goals. So the main stretch goal that we have is that we want to print something roughly 3 the times of the print volume. And that way, the astronauts printing this material don't have to babysit the 3D printer as they go through the cycles. And we also put in considerations for electronics, because that is one of the main reasons why most electronic satellites fail in orbit. And we met these design criteria through our design process. First, we went through whiteboard concept development, then we went through prototyping, and then we went through subcomponent testing, and eventually we covered manufacturing processes.
Our initial brainstorm yielded 4 solid concepts that we were interested in implementing for our own CubeSat design. From these 4 designs, we actually narrowed down our advantages, and moving forward after the first night, we only developed 2 of those designs. Those 2 designs are, the first was to print basically individual faces for these cubes and assemble them via snapbooks. And the second design was to have pre-assembled hinges on the structures themselves to reduce the assembly time and number of components. This shows our very early visual prototypes from the first night, just to kind of give you a perspective of if you couldn't visualize it before. This is actually what we're doing. The water bottle in this image is representative of a telescope. And then also you can see kind of some of these material reduction patterns that we were planning on implementing, and you'll see those in the next slide as well. So instead of printing a bunch of large assemblies and that we weren't sure whether or not they would work or fit together with one another, we decided to test the individual components before moving to the assembly level. So as you can see, we printed out individual faceplates, hinges, and snap-hooks, and tested those individually for feasibility and as well as like strength, for example, on the faceplates. one of the more notable discoveries that we gained from this method was that these hinges themselves actually could be printed in place, yielding a pre-assembled hinge right off the printer. So those are printed vertically, as you can see in, I guess, the upper left picture there. And the judges are looking at those right now. We actually have a hinge that works right off the printer. So from that component testing, we also just kind of looked at kind of a benefit analysis, where we want to move forward in our design. And I guess our two main choices were, do we want to use those snap hooks, rely on, I guess, individual plates and hook them together, or did we want to pursue the hinge design? Ultimately, we did decide to move forward with the hinges because even though they require stricter tolerances to get the clearances right, we decided that the assembly savings that they provided were a great benefit for the astronauts.
This is our final design of one unit of the cube. We will use 3 such units to form our assembly. As Nathan pointed out, the main constraint we had was to build the entire set of 3 cubes in a given volume of 10 by 10 by 14 centimeters volume. And on your right, you can see the printed configuration of this stacked structure of 4 plates. This will help save a lot of maintenance time for astronauts because they are printing everything in one single print than 3. And on the right bottom, you can see the assembled configuration. The way this works, the printed configuration can be folded out and snapped together to form a square structure first, and further supported with the help of the support plates on the top and the bottom, which also reinforce the support for the telescope. Zooming into the detailed view of the salient features we have, one of the most important features is the hinges, as Nathan pointed out. The hinges reduce the assembly time, and we are using 3D printing to our advantage here to save that much time. And we are using the traditional snap hooks to reduce the assembly time again, and there are provisions for holes on for the solar panels, and we have the optimized structure for mass reduction. So as you can see, the final assembly on the screen. So you have the 3 cubes stacked over each other. We have the provision for telescope, the bottom one for electronics, and we have the provisions on 4 sides for the solar panels. This is how the final assembly would look with the solar panels on it. So what you see here on the table is the final representation that we 3D printed. So you have this triangular structure, saving materials, the hinges, and the snap fits here. You can have a look.
Okay, so unfortunately, a purely mechanical solution may overlook one of the most common failure avenues for orbiting satellites. And that failure is called total ionizing dose. What that means is, on Earth, when charge builds up in a cloud, eventually there's enough of a voltage difference such that there's a dielectric breakdown, and that causes lightning. The same thing can happen with any sort of dielectric. And as you can see, ABS plastic is actually pretty close to air in terms of dielectric constant. So as charge accumulates on one side of the satellite from emitted particles from the sun, eventually there can be a static discharge, and that can destroy electronic components. So in our design, we've accounted for this. We've allowed for attachment points for a Faraday cage that protects all of the inside components from this sort of damage.
So now coming down to the cost, manufacturing a traditional aluminum CubeSat would take around $300,000 US, which is a way a lot of money. And if you want to make 3D printing feasible, so the raw materials weigh less than 200 grams, and the weight of the CubeSat would be also less than 1 kilogram. And the final deploying cost would be around $80,000 US, which is significantly quite less. So it's wiser to manufacture the CubeSat on ISS rather than sending them from the Earth, which costs us a lot and saves material, time, money of the astronauts and the space research as well. Do you have any questions?
Let's walk through that previous slide one more time. If it's 3D printed on Earth using ABS and shipped up, what's the difference between you shipping the raw ABS and printing on the space station? I'm just running through this because, it's mass is not created or destroyed really during the process. So I mean, you're going to have to pay to lift all that ABS up anyway. So I'm not really following this.
One of the major advantages to printing it from space is that you can use a more minimal structure, I guess. You're only looking at a 45 Newton deployment force off of the space station, as opposed to, I don't have the number for off of, if you launch the same structure off of Earth. But the current CubeSats that are manufactured out of aluminum or steel, they have to be built to be a lot stronger because they are launched off of Earth. And that's the same package that goes from all the way to launch up to the space station and then deployed from the space station. So essentially what we're doing, yes, we still do have to send all of the materials up, but it is fewer material, less material because we don't have to include some of that packing.
The packing to protect it during launch.
Yes, exactly.
That's where the savings is.
Yes.
And you still have to launch all the optics and electronics.
Precisely.
You're not proposing printing the boards in space?
No, the satellite and the electronics and the solar panels are still need to be launched from Earth.
In pieces, then assembled on the ISS?
Yes, precisely.
What percent fill did you use for your prep?
I don't know that number.
Oh, what percent fill?
Yeah, what percent fill on your printer?
So we for initial prototypes we use a 20% fill on our printer, and I'm not sure about the final build we have. So I think the final build is much more denser compared to the initial prototypes, the pieces you can see.
Yeah, and you were trying to optimize what the amount of material used versus the strength requirements that you had.
Yes.
I mean, just off field, this is the strongest one that you printed. I'm assuming you used 20% fill for all the prints.
Yes,
right?
all the parts you're holding are filled, were printed with 20% filling.
Okay, but you chose not this one because this was too much material compared with this?
Yes, this was doing the job because the 45 Newton force was very less, and we tested with the weights, and it was doing a pretty good job.
Okay. Anybody else? Yeah, Ken.
Will this kind of plastic off-gas much in a vacuum, or is it pretty stable? Off-gassing is when the plastic starts to decompose in a vacuum. And with a telescope, you might worry that some of that contaminant could get on your lenses and things. So it's good to have structural components that are stable in a vacuum. And I just wondered if that was something that you guys thought.
It wasn't really explained to us, that concept, so we didn't account for it in the design.
Did you consider other designs different than a cube design, like a hexagon cross-section?
The reason we chose the cube design was perfectly fitting in the given volume without any problem actually. So we had only 140 mm of length. So we had to accomplish the, we have some 3D printing limitations such that we cannot go over a 45-degree overhang. If you use a hexagon, it would be a 60-degree overhang. So that is another problem. So the best design was to use 3D printing to our advantage and print it straight up on the 3D printer.
Okay. Unless y'all have any other burning questions, we kind of need to move on.
How long do you think it would take to assemble your design?
One of these cubes took approximately, all said and done, about 30 seconds. And then so 3, so 90 seconds. It's relatively short.
It is 9 steps. It will take 9 steps for astronaut to completely assemble the cube without, not considering the electronics and telescopes, just the structure. It will take approximately 9 steps.
Okay, thanks very much. Back or having a hard time hearing.
Okay.
The first human space launch was 20 years ago, and still, astronauts have problems dealing with the microgravity. In this environment, it is not possible to keep items stationary without the help of restraints. This has led to the use of Velcro in many facets of daily human life on the International Space Station. For example, Sunita Williams gets a hairbrush from the Velcro compartment, but cannot brush her hair without hitting the door. Even Chris Hadfield cannot make a simple meal without an ingredient floating away. Introducing AstroLog, an expandable device that can be used by astronauts and even people on Earth to hold and organize their items in a convenient manner. It can expand to a full 48 centimeters and collapse to only 14 centimeters, even while holding various adjustable clips. The open-faced outer box design allows for more portability even while tools are attached. AstroLog, secure your space.
All right, so as you can see, we're group AstroLog. We're actually crew convenience. So our needs statement wanted us to design a reliable, versatile, non-intrusive, space-efficient organizing equipment. So I'll leave it up to my teammates. My name is Christian Estella.
And I'm Kelsey Fiesler.
Andres Gutierrez.
I'm Dino Yeager.
Deepak Dankani. Kenneth Ho.
So, next slide, please. As you can see, our here multi-dock system that is portable, ergonomic, and reliable.
Okay, so our needs statement was very open-ended, and so for our design, we wanted to make this as easy as possible for the astronauts. So our requirements for our design were that it was ergonomic, easy to use, portable, easy to carry around, versatile, meaning it could hold a number of tools, and easy to assemble. During our product design, we were working with a number of constraints. The first constraint was time. We only had 48 hours to design and fabricate this. Our second constraint was material. We could only use ABS plastic along with paper and tape to construct our design. Our third constraint was the number of prints. We were only allowed to use one print, and there could be no support structures in that print. And actually, all our designs were able to fit in all our parts were able to fit in a single print. So starting out, we started with this prototype when we were brainstorming, and we ended up with this. So when we were first considering our ideas, we thought that a triangle would maybe conserve space, but we discarded this idea because we thought that a triangle with sharp edges floating in space might be a safety concern. We also considered rotating parts to conserve space, but we also thought this wasn't such a great idea because rotating parts and microgravity could be a little cumbersome. And so Deepak is going to explain a little bit about our final design that we chose.
Thank you. So as you saw in the video, we have a telescoping mechanism that we're using to expand our restraining device to allow more tools to be set. So we have a T-groove running from the right end to the left end, which could be used to enter the restraining fixtures and slide all the way in. And we have enough clearance for them to slide around, but not so much for them to come out, rotate and come out of the device. So the main concern was multi-utility, so that we could use a bunch of we could store small and mid-sized objects in the device. So but working in microgravity, most of the locking mechanisms that we use are in some way or the other connected with gravity, so we didn't want to use the traditional ones. ABS plastic, so in microgravity, we used ABS plastic as to our advantage. First of all, no weight or very less weight, whatever. So we didn't have to put a lot of concern into if they'll hold up, if they'll break. That was not our concern. Secondly, the ABS plastic is elastic. It's tough between 20 to 80 degrees Celsius. temperature range, and its impact resistance. So we decided to mainly take advantage of the elasticity for them to clamp on, for the fixtures to clamp onto mid-sized and small objects. So the first fixture that you see on the left is a tool holder. So suppose an astronaut is using a bunch of tools, he's working on a project. He or she could clamp it onto a hammer hand, a wrench, a bunch of tools in there. So, and hammer handle, I'm sorry. And then the second one can be used to snap a pen connection. So basically you put the pen in and then snap it up. Any kind of small tool stationery. It could also be used for any string loop, to store any string loops. The third connection is similar to the second one, the third one from the left. It has a locking mechanism. So as you know, large objects still have inertia in space, although not minimal weight. So we would use that to, put it into a string loop and then push the end so that it locks behind the hook. The fourth one is can be used as a paper clip to hold up to documents, instruction sheets, food packages, and liquid bags.
Thank you, Deepak. So I'm going to basically sum up everything about the AstroLog. The first thing, like Daniel said, it has an innovative telescoping mechanism. Basically, it can extend up to 48 centimeters to 14 centimeters. It's also very space efficient. It's about the size of my hand, specifically about 4 centimeters by 6.5 by 14. So it's very small. You can carry anything with it. It's also easy to use, able to collapse and expand. And it also has, like Deepak said, multi-purpose restraining tools. I just passed a couple of the heads around that could hold several items. And we also designed a clip. So if you wanted to bring anything portable, you can clip it onto your belt. Okay. And our plan was for when the astronauts finished printing this, since there's a lot of Velcro around the space station, we were planning to attach it to the side, and whenever you want to use a restroom or something and you need to bring certain materials, you could expand it, hook it on with the Velcros, and then clip on whatever you need to hold. For example, you're brushing your teeth, you might need to hold something with toothpaste or like the toothbrush or whatever you need. So it's very convenient, and I'm gonna let Andreas talk about the potential uses for this device.
So even though it was a 48-hour design challenge, our main use was providing value to our end customer, who is an astronaut. We discussed with other astronauts, and we devised all of these potential uses that will be in the future be used. So if we decide to print AstroLog tomorrow, any astronaut could be taking use of medicine. Whenever an astronaut needs to take its blood, he needs to juggle between different equipment and different instruments. So this is going to provide the user, they're going to touch the syringe attached to the other bags, and it can use the two hands and extend the reach of its purpose. Food preparation. As we can see on the picture on the left, we see different food bags. Whenever they're preparing, as we can see in the video, they have to juggle around with different ingredients. So having AstroLog at the disposal, you can use it and you can put the different ingredients on top of it and keep preparing what you need to do. Tool arrangement. As we can see on the right, we figured out two different types and two different clamps of holding tools. So we can have small tools and medium-sized tools. So we can hold different type of equipment. We can also use it for laboratory use, so you don't hit yourself with a brush whenever you're trying to do certain things in the laboratory. And room organization and overall restrainment. So anything you want can be kept to the wall. And as we talked, if you were to print two astrologs, you can keep anything attached to the wall. And the only limit is imagination for that use. We want to say special thanks to these people, and they have truly guided us, and we're truly thankful for all the help throughout these 48 hours. And we wanted to say the special thanks to all of them. I wanted to say at the end, AstroLog is a time-saving device. And in space, every second counts. Thank you very much.
What questions do you all have? Please.
Is this left-handed or right-handed?
Sorry?
It could be either or.
It could be either
Which
or.
one? Yes, sir. It could be either
It
or.
could be either or.
Because you could rotate it any way. It's completely multi-directional as well.
And if I may, a second question is, describe an awkward moment during these 48 hours in your team.
An awkward moment?
So the hardest part of designing this was the telescoping mechanism. We actually went through a lot of trials just to get that done. And the first time we did it, it didn't go through. And then the second time we did it, when we put it through, it slipped out, so it wouldn't hold. And then finally on the third one, thanks to Daniel, he made a groove at the end of each one and allowed it to pull out and stick, actually, like hold in place while you stretched it. And when you closed, it wouldn't come out. So that was like, I guess, the weirdest moment.
Yeah. 8 hours sprinting and then boop, falling off.
So your initial concept and your final concept looked a whole lot alike, but you talked about a couple other concepts that were radically different. How did that fit in?
We had this one. So this was pretty much like the one that we finished with. The only thing is that we wanted it to be closed-ended. But after thinking about it, we also wanted to be the tools to be so you know what's in it. So that's why we left one side open. Another one that we had was this other idea, which was very interesting. The problem were edges, so triangles, they're very dangerous, as well as the fact that we couldn't get the mechanism into this.
We decided on a square rod instead of a circular rod because we didn't want to rotate.
We wanted to rotate it, but we didn't take into account inertia. So we don't want to move it and then for it to keep on
Tools
spinning.
sticking out at you, we thought that would be.
And the property rights with the Mitsubishi logo.
2 more questions.
Yes.
Let's go back to need statement. Why is this better than just a strip of Velcro?
Because
excellent question.
Yeah.
When you use Velcro, you have to have something with Velcro.
Sure. So I just stick Velcro on it. I mean, I've got to have a hook, a loophole or a hook.
A great thing about this is that if you want to move things from one wall to another, you don't want to be having to pick one at a time. You just want to take it all out, move it to another place. And that's the facility of this. You can just take everything that you have in one wall or in one specific place and just move it conveniently to another one.
Also, what if you're working with you just printed out a paper and you're following instructions to repair something, you don't have a Velcro on a piece of paper. So stuff like that. It's
Also, one of the issues was the wet shirts that were on the space. Normally, the astronauts just hang them around and they go loose and people get hit on the face. So if you have AstroLog, that's where we expanded it to use. You can just attach it to the wall, and you don't need that much Velcro to do that. So you will expand the use of anything you could think of.
Okay.
You had a question. Yeah, so I appreciate the sort of human factors arguing against the triangle one and pointing. Yeah. But I'm kind of looking at this, and these guys like hanging out here seem almost equally like people. There'd be some objections to them.
It's going to be hooked onto the belt, so we didn't really think it would be a problem.
Yeah, and we can always put a bigger chamfer and round edges off or shorten, the height. That's just minor design considerations we need to make. If we are looking at if safety is such a major factor in specific conditions, but worthy to consider.
Okay.
Any other questions?
Thank y'all very much.
It's Brenda Lopez, and I'm an electrical engineer.
Harman Chalba, I'm a MET.
At this Aggies Invent we choose the Mars mission task for our task. And this task asks us to design a device or communicator by using the camera movement. Now I will show you the video, brief video about our project.
In today's world, with billions of people, where communication has become as quick as a text, cities never sleep, and everyone is constantly on the go, we have overcomplicated life. Too many connections, too many bonds, too many things around us. Sometimes, all that we need is a momentary escape, just one moment of silence. But it isn't until the moment when you're in complete isolation, stranded by yourself, that one realizes just how important communication is. Perpetual isolation can drive just about anyone crazy, especially when you're all alone on a remote planet with 7 billion people inside, but not a soul to talk to.
Alright, so to make sense of this project, basically how we got to this project was it's based upon a book called The Martian by Andy Weir, and with this, what basically happens is that this astronaut, Watney, he goes in on a mission to Mars, but things don't go so well. When he gets there, he loses connection electronically with everyone basically off the face of the earth. So he's 140 miles away from Earth with no one to communicate with. There's no text messaging, no internet, no way for contact, no emails. Like, he is basically hopeless on Mars. And so when things seem to be getting worse, he comes upon a salvaged Mars Pathfinder probe, but it's not fully functional. The only function that is able to still do is its camera. This is basically like the camera, this part and this. And how it works is it can only rotate 180 degrees this way, 180 degrees the other direction, and only about 85 degrees upward and about 75 downward. So that's the only thing he has to work with to communicate with Earth. So with the solution that was found in the book was that he was able to lay cards out and to communicate. Only the space station could receive his pictures, but he couldn't understand what they were telling him. So in order for them to communicate, he would lay out cards and they would rotate the camera in the direction of what the letters that they wanted to send him. And so how he would record this is he would inscribe on the dirt of Mars and inscribe exactly what letter after letter after letter. And so of course this is time consuming, and it's not exactly the most effective solution for this type of setting. So as you can see here, this is basically the space probe, and in the center is the small camera, the only part of it that works. So our requirement for our project exactly is to create a more quick solution that can actually record the messages so that he doesn't have to be there with the camera 24/7 in order to receive the messages, and it has to be easy to use even with his spacesuit on, and it has to be able to work even with the different atmospheric weather and pressures and all that stuff. It has to be portable, and it also has to, instead of the limited space it has on the ground to just inscribe on the dirt each letter, it has to be able to record more than just a phrase. however long the space station needs to communicate with this astronaut. So this was basically the temporary solution. He would go inside and write something, and then he'd go outside, place it on there, and they would turn the camera so that the space station communicate back to the astronaut. And so, of course, this took a lot of time. And so with our solution.
All right, I'm going to take over and talk more about the technical aspects of our proposed solution and how we ended up making it. So, as in the book, the character lays down the cards, rotates the camera towards them. The controller controls the camera. The controller is back at Earth, and in order to communicate, he controls the camera, moves it, points it towards the card that's placed on the ground, and then letter by letter, he forms a sentence. First, that requires the person to be in spacesuit on the surface, and it's really time-consuming. So what we wanted to make was a mechanical translator and a decoder. That's its essence. The only parts, so the third picture that you see on your screen, the one with the eyes for lenses, that's what's provided. That's the camera on the Pathfinder probe. The first two images are the gear and rail assembly that we manufacture, and the rack assembly we manufacture, and the second is the gear roll binder assembly. I'll talk more about it. Then we had to decide what mode are we going to communicate it in. What are we going to make sense of those angular moments? These are the only thing we're receiving as an astronaut on space. Like angular moments of the camera, like 60-degree rotation towards along y-axis. What does it mean? We had to translate it into a symbol to make sense of it. So we went over 3 different sorts of Unicodes that we could use: Braille, Morse code, and a waveform. The waveform, that mechanism does not rely on a puncher base, a hammerhead, so we don't have to print that part. That's the first one we considered. Later we ruled it out. I'm going to tell you why. So in the waveform mechanism, you can have a pen or a Sharpie or any writing instrument sticking out of it and use the angular rotation along this axis to inscribe a line on the paper binder, on the paper that's held in the paper binder. What happens when you inscribe a line and then you translate the paper? You generate a wave. With every wavefront with a particular amplitude and a particular wavelength can be translated into a different symbol. But in that case, you have to establish the Unicode. Not too hard to do, because you can establish an arithmetic progression with where every point, let's say where every one angular rotation takes you to the next letter in the series. Not the hardest part, but pens are unreliable, and also something that we don't know if he has access to all the time and if he can use it. So we came up with a mechanical device that does not rely on having a pen or a Sharpie. So we totally went with Morse and Braille because they can be produced with a puncher-based mechanism, only with the use of the hammerhead. So as you can see in the assembly, take it back. Yeah, as you can see in the assembly, that gear causes converts the rotational motion of the angular rotational motion to the translation of the hammerhead. That the green thing, that's going to be our hammerhead. It's just going to be pointing at one end. And in the other parts in the exploder assembly that I'm going to go over is the axle, the two gears that you see at the top. They're going to be punched into a paper and rotation along this axis. That's going to translate the paper along that line, just like you would do in a dot matrix printer or an old typewriter, where you would have 2 dots at the end. That's because the binder would have 2 gears at the end, and it would rotate and feed the paper. Benefits. The biggest benefit, you don't have to be present on the surface. This thing will record messages for you. Totally. You don't have to be present there. It will keep a track of the recorded messages. The only limiting factor will be how fast you can generate is the angular velocity of the camera, which is on the Pathfinder probe, and the amount of paper you have access to, which we are assuming, and we are also doing the assumption that we have quite a lot of paper, and duct tape is the only things that we can use. So that wasn't really a problem for us. You don't need a pen. All the decoding can be done in the HAV unit. This is the unit the astronaut's going to be when he's not outside. So limited interaction beyond our project. So one more important thing that we considered was when we are designing something to be 3D printed, a really important factor that we want to pay attention on is the reusability of each individual project that individual part that you print. What we are printing is just an assembly of gears, axles, racks, all the parts that can be printed and reused for many applications. Thank you.
Oh. Thank you. everybody. Yeah, go ahead.
So the dot matrix paper was that like? Are we going to bring dot matrix paper to Mars?
No, we just said sheets of paper.
Just the sheets of paper. The binder will fit in. The binder will pierce itself.
That seems like a pretty integral to your solution. Having that.
Yeah, well, yeah, it has to pierce through the paper, and then when it's rotating, that has to translate into translatory motion. It has to linearly forward the paper.
Any other questions? Yeah.
Is it possible to transmit emotion through this device?
Well, if it is what?
Emotion.
If it is possible to transmit emotions through text, then yes. Similar, same process, same way.
Okay.
Can decode it. If someone really wants, if you can make sense of what they say and what intent they wrote that message with, then I guess you can relate with the person who wrote that message. You can make sense of it and what emotions were put into writing it. It's more like a personal thing.
Okay, thanks very much.
My name is Joe Kerwin, and I am one of 8 kids from Illinois. Being a doctor, and I was the doctor on my crew too, I thought, what medical equipment did we have that it would be very handy on a long mission to be able to build your own spares instead of having to package them and carry them up from the ground? And there was a pretty long list, but one of the most intriguing ones was the Foley catheter. It's frequently used in moderate to severe medical cases, and if we're going to Mars, there will be 1 or more Foley catheters in the medical kit, no doubt about it. And it's such an easy thing to fix if you have the proper equipment, but it can be fatal if not. Now, if I was the doctor in the space going to Mars, I wouldn't let the bladder burst, but if I didn't have a catheter, I would have to surgically go in with all the possibilities of infection and bleeding and complications that would cause. I'd much rather have a catheter. If we can migrate to doing things in orbit rather than on the ground, we're going to be able to do more and do it better and save money.
I'm Jane.
I'm Robert. And I'm Jacob.
And we are Starfleet Medical. We were tasked to build or design a 3D printable Foley catheter by Dr. Kerwin to print onboard the ISS in case there's a need for replacement. And as stated by Kylie Ryan, it's not a frequent problem, but it is a huge problem if it does occur. And when you're in space, microgravity changes the way that you feel the urine flow in your bladder. So when your bladder is super full there, you can't really tell that you need to go and relieve yourself, which means that a lot of astronauts don't go to the bathroom as frequently, and it results in urinary tract infections, kidney failure, a burst bladder, or death. And when you're inserting a catheter, you take this tip and you insert it into the urethra, and once it reaches your bladder, there's a balloon here that expands and it anchors that balloon. Yeah. It expands and it anchors the catheter into the bladder. And once that is filled,
there's a hole in the tip that drains urine from the tip of the catheter into a drainage port here that is connected to a bag like this.
So there are two main types of catheters. There's the Foley catheter, which we've been discussing, which we were tasked with designing. There's also a straight catheter. And so the advantage of using a Foley catheter is it can be anchored in place by the balloon for up to 30 days. Whereas the straight catheter is a single-use catheter. You put it in, you evacuate the bladder, and you remove it. And so in terms of space travel, you'd have to take many of these to do the same job as one Foley catheter. And then some of the constraints we had to look at, since it is a medical device, we needed to be able to produce a sterile device that could contain bodily fluids. It had to be flexible to comply to the patient's physiology, and it had to be biocompatible. And then the two big constraints that we had to deal with were we had to 3D print something that could be anchored and then removed, which was crucial. And so since we were 3D printing in plastic, we initially thought we couldn't do the balloon method, so we came up with 3 different ideas. So our first idea is a sort of a mesh that can be collapsed and then expanded. And so you collapse it to insert it into the bladder, similar to a cardiac stent seen in that picture. And then once it's reached the bladder, you expand it to anchor it in place, and then you can contract it and bring it back out. The second idea was kind of a wing method where you insert it into the bladder, sort of like this, and then once it's reached the cavity, it'll naturally expand, anchoring it in place. And then when you would like to remove it, you simply tug on it, and the Y shape will allow the two wings to come back together. And then our third option was using shape memory polymers, which when subject to a stimulus such as light or heat, will change shape. And so we would initially have the shape be a straight rod, similar to these catheters on the table. And when you insert it and then apply a stimulus, it'll change to this spiral shape seen in the picture on the slide. And on the second day, we actually realized that there are companies printing in silicone. And so we could revert back to the balloon method, which we're going to talk about now.
So the silicone that's been used in these 3D printers before is actually a medical grade silicone. This material already exists. There's no research and development that has to be done. You just use the material as is. And so using this material to 3D print, what sort of constraints are different from 3D printing compared to typical manufacturing methods that are done here on Earth? So in order to accomplish these objectives, there's a few things that we had to change about our design compared to a typical Foley catheter design. Primarily the inflation port, where the balloon is inflated, as well as the geometry of the balloon itself. And the material that's used for the Foley catheters, the medical grade silicone, won't have to just be used for these catheters on the space station or in future missions. It can be used for a variety of medical applications that are use silicones. And most interestingly of that would be 3D printing contact lenses as well. So this is the final design on the screen for the Foley catheter we have. We also have a 3D model that we printed in the plastic, if you'd like to pass that around. Obviously, you don't want the plastic to be used, but some of the dimensions that are used are the overall length of the tube itself, not including the ports, is 412 millimeters. This meets the design constraints that were given to us by Dr. Kerwin. And what's really nice about this piece in particular is it's printed in one go and one material. There's no assembly required. What's really nice about that is it simplifies the design and also requires no assembly once it's removed from the 3D printer. It can be used as is, or it can be stored immediately, less handling required, and less complications from that. And it all fits within the constraints as well of the bounding box that was given to us. So on the left screen is a typical Foley catheter geometry that's used. The larger port is where the urine is drained down to the collection bag, and the smaller port that you see on the top, that's where the saline solution that inflates the balloon flows through. And on the right is the port itself. It's the large end that hangs, that is outside of the body. And the bottom is the collection port where the bag is attached to and the urine drains. So the urine will flow through this larger hole, that's the larger port there, and flows into the bag for collection. And what's different about our design, what I mentioned earlier, is how the inflation process is done. So the top port is where the inflation takes place. So a typical Foley catheter, including the one that we have up here, uses a spring check valve to allow the saline to be inserted and removed from the system. So something we did to simplify our design, we don't have to have different materials, we don't have to print multiple components, because we printed it all just in silicone. So it's a silicone barrier that can be pierced with a needle, similar to how a medicine bottle has a cap that can be pierced to have the medicine extruded with a syringe. So we can insert the saline with the syringe, remove the syringe, it seals itself with the silicone barrier. And whenever we need to remove the fluid, we just repeat the process to drain it as well. And so the other thing that's different about our design is the catheter balloon itself. So it's kind of hard to see. I'm sorry if it's difficult to tell. On the left side is the side view of the balloon area of the catheter port. There's a very small geometry in the top left corner there. And this is a thin wall of silicone material, and there's a port there where the silicone inflation port runs to. And whenever the silicone reaches there, it expands and 360 degrees and basically anchors the catheter in place. So what's different about our design, because of the 3D printing, is that we need to have a flat base for the material to be printed on. So we can't have this hollow concentric ring completely around. So we instead printed it 230 degrees. It'll still inflate to enough capacity to be able to hold the catheter in place.
Okay, so some of the limitations include sterilization, because while it is printed sterile, you can't store it in a sterile environment. You would have to take it off and use it immediately for its purpose. Also, the small dimensions lead to a possibility of maybe having something messed up in the printing. Some of our future work that we're excited about is the idea of printing it inside of a sterile pouch, which is already being done with 3D printing food. It'll be printed inside the bag, and then you can take it out and the bag will actually double as the collection bag. So that's something in our future that we hope to do. And another thing would be, since we only used one material and our constraint was that we could use two, we would hope to use the second material as a hydrophilic coating on the catheter, which acts to take the place of a lubricant. And so if you get the catheter wet, if it has this coating on it, then it'll do that purpose without needing any extra material. And so we'd like to thank the entire EIC community, and especially Joe Kerwin, Kylie Brent, and Ann and Rodney Same.
Any questions?
In looking at the silicone printing, did they say anything about how much flexibility is retained once it's printed?
Well, yes, they've actually, the primary use for that now is printing breast implants, which need to be malleable. So yes, it is flexible.
Let me ask the same question that was asked before. Why not manufacturing it on Earth and then transport? What is your answer?
So we've just, because it is an uncommon thing, they don't anticipate it happening, and so they don't want, and they don't know how many they will need. So you may need a lot, or you may not need any. And because of that, we thought it'd be best to just have it where you print it if the need arises.
How far did you get with an ABS solution before you kind of pivoted to the silicone?
We made it to about the first night is when we started to really kind of come up with some ideas, especially with some like collapsible geometry. And then I think later that night is when we started to find some of the silicone thing, but we really didn't know enough about it to carry a whole lot further. And I think after we all kind of slept on it, had all these ideas floating around in the head, we came back and just more or less returned to the balloon idea, especially going back to the one material type manufacturing.
We had other materials we were considering, but not, that wouldn't work with the balloon, but would be a smooth, biocompatible material to 3D print.
Last question. Are there any major extruder modifications necessary to print with silicone?
Yeah, I think so. There's only one company that's making it right now. Actually, there's two, but the one that does the medical grade products is in the UK. And they, as you can read on their profile, there's a lot of changes that they've made so that you can extrude silicone.
I think silicone's a thermoset.
Was it?
I think it's silicone a thermoset, or is it?
It can either cure in air or UV.
Yeah, so it's a thermoset, so it's a pretty major.
Yeah, it's a major one.
Yeah.
Okay. All right. Thanks very much. Appreciate it.
So as it works right now, in order to get drinkable water or fluids into space, you have to ship up. And it's a single-use thing, and it creates lots of trash. So the idea is, as we progress into the space industry and space tourism, it's kind of inconvenient to have to ship these up with a bottle and an insert in the bottle top in order to drink a soda or root beer in space.
Okay. That's what we're looking at. That's what we want. See those two? That's exactly what we want. That's a successful test right there.
SpaceSip is a 3D printed bottle cap designed especially for space use. A 3D printed insert which utilizes a liquid surface tension to move it to the top of a bottle. We have created a sustainable, recyclable, and money-saving method that can potentially become the backbone to space travel.
Okay, so this device allows you to control the flow of the whisk. You can either have it in an open or a closed position, and right now it's in the closed position, and you can see it blocks all the flow from coming out of the cap. Basic sliding mechanism. Right now it's closed, and if you slide it, it opens, and that allows the flow to come up through the whisk and out the top.
SpaceSip, and my name's Julio Gonzalez.
I'm Victor Trujillo.
Evan Gonzalez.
Alex Jennings.
Brian Garlett.
I'm Nate Pearson.
Be sure to speak up. Our mission is to design a revolutionary recyclable system for Earth-like drinking in a microgravity environment.
Alright, so by a show of hands, can I just see how many people like Capri Sun? Alright, so right now, how astronauts drink like fluids in space, essentially through a Capri Sun pouch, which is like what I have right here. This is like a model of what they have. So it's essentially just it's a system that is a one-time use. It works by just puncturing through the top, adding the water, and then putting the straw in and just drinking from it. So this is good and bad, I mean, in the aspect. It gets the job done, but there's a problem with it. There's two small problems, I guess. One, that it just spills, and it spill a bit. And the other problem is that it produces waste. So the numbers you see on like the chart right there are how much it actually costs to send the straws and like the pouch into space. That's over a 10-year period. So in 1 year, we spent about $1.4 million just to send a straw and a pouch to space. So how can we reduce those numbers? The way we can do it is by 3D printing. So if we design a device or a system that can be printed and have multiple iterations, it can be printed multiple times, it could reduce the cost of shipping into space. So the way we would do this would be in 3 simple steps, essentially: print, drink, and recycle. With the print, the astronauts could print like so they can print a cap, an insert, and a bottle essentially in the future. And this would allow them to print it multiple times and whenever they would want to. So with drinking is that the astronauts can fill their receptacle, their bottle, with pouch, whatever they print essentially, with the liquid, the beverage of their choice, and put the insert in there, and then put the cap on there and drink like they would on Earth. It would represent like drinking out of a water bottle at home. And with that also, since it has like it can be sealed, they can move around the space station, and it's recyclable. So everything that they create can be melted down, and they can reuse it again to create more caps and inserts.
Awesome. So one of our primary objectives in designing this whole project was to make it more Earth-like when you're drinking. So one of the things we wanted to try to avoid was using a straw like they do currently on the space station, because let's face it, get paired with Sabre Astronautics and their president, Dr. Jason Held. He was our teammate and mentor. And what Sabre Astronautics has going on, you guys saw in the video, they have this cool insert, and it can fit to pretty much any bottle. You just drop it in, it doesn't attach to anything. And it brings the fluid from the bottom of the container to the top of the container. Previously, they had to suck because of the microgravity. How you normally get water from a water bottle to your mouth is by drinking it, and the gravity falls in. So what this thing is, unfortunately, although I know that Aggies don't lie, cheat, or steal, we can't show you the specs because it's pretty confidential. But as we explained in the video, it's just the surface tension of the water combined with the high surface energy of the material of the insert allows the flow, a driving force to push the liquid to the top.
Now, the problem, and this has been tested, they did it in some parabolic space flights, as you saw, and it's proven that it actually does work. The problem, though, is that once the flow starts, it doesn't really stop. So we were tasked with finding a solution to that. So
Okay, so to restate the problem, the wick is good, but there's no way to stop the flow. So we created a two-piece bottle cap, and we made it fit for our design to a normal soda thing. And so the two parts, you can see, they get inserted to each other. It slides, and it either allows or restricts the flow based on the orientation of the smaller funnel. And that allows the trickle flow of the wick to get into that funnel. And when liquid goes in through those holes, the surface tension in the funnel keeps it together. And so it allows you, the combination of those two things allow you to sip like you would on Earth.
Okay, so why 3D print? So our system is a recyclable system. So you create your product, you use your product, and then you melt your product back into its original feedstock. So what that does, that only requires one material launch. So instead of having, say, 4 resupply missions, you're only going to have 1. And because you're reducing the plastic bags, the straws, and a bunch of other stuff that can just be simply printed on the International Space Station. So another perk is that you can send our designs electronically. So you could, so let's say you wanted to have an experiment on a pressure vessel. You wanted to see how a fluid acts in some awkward container. What you could do, you could take our product. All you would have to do is change, say, the threads on our CAD file, and you could have any experiment from anywhere else in the world. So finally, our product is needed for long-term space travel. If you want to send someone to Mars, you do not want to make them drink out of a plastic bag with a straw the entire way. That's inhumane. It is. So that is why our product is needed on the International Space Station today.
So in terms of revenue model, there's kind of 2 main things. One is savings and one is earnings. In terms of savings, you're reducing your manufacturing costs considerably. You don't have to have them made on Earth. So the cost of 3D printing this material takes a very small amount of material. Our cap is almost immeasurable. It's just this tiny piece of plastic. And of course, the insert is also 3D printed. So that's the SpaceSip piece. It's 3D printed as well. It doesn't use very much either. And any bottle designs in the future would use more. But in general, we're talking about considerably reduced manufacturing costs. And then also the operating cost for your mission is considerably reduced as well by the recycling system that we would like to implement with this, or that this would be used in complement with. So you're shipping up your materials one time, and then you can almost indefinitely recreate as needed these parts. When you recreate these pieces, the recreation process was to sterilize them. So you're basically creating an infinite cycle on one shipment of plastic, or close to an infinite cycle. So in terms of earnings, then you also have licensing, everyone's favorite 21st century first world country income source. Make something once, license it an infinite number of times. So that's a great income there. And then Four Pines Brewing is an example of other potential Earth applications. Our partners, State AstroLog, have an agreement with Four Pines Brewing for distributing and marketing beer here on Earth. It's an Australian brewing company that would include these inserts and potentially our caps as well. To not only an income source, but also to garner excitement about space and 3D printing in space, technology in space, and the future of the industry in general. So just a brief overview of the timeline of this idea and SpaceSip as well. In June of 2014 was when SpaceSip demonstrated their product, the insert, the wicking insert, for the Earth-like drinking experience. And then, of course, right now is when we've designed and tested our product. We would hope that within 6 months we could have a fully functional system, which would include a bottle design or a container design at least, whether a bottle or a sack would be, maybe a bladder would be ideal, something to that effect. And then looking forward in the future, hopefully within a year's time or less, we could have tested sufficiently in space, having printed the product, and phase out the current method of sending up the drinking bags and straws, and have ours completely take hold of the drinking in space. And we'd like to give special thanks to Dr. Jason Held in Australia, Sydney. He was very helpful in the process of this. He's the CEO of Sabre Astronaut, and as well as Greg Chomtoff, who was exceedingly helpful. Thank you so much for your help. And then, of course, all the staff here at the Engineering Innovation Center.
Questions? So you said that if I'm understanding correctly, in your cap, you're getting sort of black box liquid that has some force behind it, and then the liquid's going in my mouth by a capillary action between a couple of surfaces. Is that kind of the basic principle behind it?
Yeah, so his wicking mechanism insert will draw it up, and if we provide a way to control that flow, the surface tension on our funnel shape should be able to keep it in that area as almost like a bubble.
So am I still like sucking off of this thing, or am I?
You're not
able
sucking.
to.
It's more of sipping. It's more of like a sipping. Like it holds it to where the point where like if you drink, it'll like keep on flowing, but if you stop, it holds it because of the surface tension.
Okay.
So you don't have to use two hands to open it and shut it or anything like that. You can just hold it, and it'll just keep refilling on its own.
If you want to completely shut it, you have to use the tab on the top to slide it into the closed position.
Which could be done with one hand.
Yeah.
It'd be a thumb switch is the idea.
So, and what kind of flow rate can you get out of this? You know, the straw, you can get a really high flow rate. So if you want to finish a bag of juice, you can get through it really quick.
Yeah. So when they did the parabolic flight test, they found that it was a steady trickle. It's not exceptionally fast, the motion that it comes up.
So it's great for sipping.
It's great for sipping. We don't actually have any measurements. I don't think they took any measurements, and even if they did, they'd probably be confidential.
Cappuccino machine.
Yeah.
Time for one more question. There is.
Now, you did the 3D printing here on Earth. How would it be done in space? Do you know? How is a 3D printer in space going to work? Because let's say you deposit this because gravity, you melt the plastic and then it gets deposited, and then you go and you build the 3D object.
I believe what we came up with was that actually in space it would kind of actually go towards our benefit because the pieces that we were printing were so thin that they kept on collapsing on themselves. So once in space, I believe when we spoke with Jason, he told us that that would actually help because since there's no gravity pulling it down, it would be easier for it to be printed out.
And current space 3D printing technology, just to right, I believe is the man behind that. So Made in Space has a printer there actively that is being tested and seems to be presenting good results. So in terms of just in general, that's already underway. 3D printing is happening in space and it seems to be working.
Okay, thank y'all very much.
Howdy. All right, guys. Well, like Rodney said, we're Direct to Mars, and here we're going to present to you a small video to put you in perspective, to take you into our minds of what we were thinking while designing this product. But not to get to the stuff. So I'll introduce myself first. My name is Gilberto Arispe.
My name is Iskandar Lamri.
My name is Carlos Mejia.
My name is Milan Pandya.
And my name is Matt Ragland.
My name is Fuguasang.
And through these next few minutes, we'll be taking you through our Aggies Invent. So to give you guys a little bit of an overview of what I'm going to go through right now, we're going to go through first the problem statement. And the admin went through this problem and took a look at it and made it ours. And took a look at it and defined it a problem for us to solve. Of course, and then we move on to some brainstorming, a little bit of calculations because everybody loves math and needs it, drafting, printing, and testing because we're engineers, and finally, our final product. So here, a little bit of depiction of our problem statement. Let's put you guys, just like in the video, out in interplanetary mission, something that's not here on Earth, maybe in the moon, maybe at Mars. We are heavily reliable. We heavily rely on communication, not only here in the Earth, but everywhere, to be able to communicate back to our mission. So within the case that communications, in the emergency that they come down due to a Mars windstorm or maybe an asteroid, just like in the video, hits and takes down your satellite, well, what's the problem? We have no communication, but with the availability that NASA gives us with 3D printing in space, we give you our solution now, which is going to be a communications antenna as presented here that is easily printable, deployable with interchangeable parts that provides a simple solution within hours to reestablish your communication with the rest of the team. Now let me pass it off to Iskandar.
Hi. So to create our product, so we had to go through a brainstorming session. So first we had to go through the problem statement that was provided by the Aggies Invent committee. So we basically went through and read it, and then we come up with some ideas, and we talked with our mentor, Dan, over Skype. So, and then we developed multiple solutions, and we were trying to analyze each solution. Later on, we selected the best alternative, and we developed our working strategy. So after the brainstorming session, we came up with 3 different designs. So the first one was a foldable antenna. So basically, we'll have like it will be like an umbrella, and we could fold it and unfold it whenever you need. This design is very hard to manufacture since there will be multiple moving parts and there will be some ball gearing, and so we disregarded this design. The second one is called we have a center ring and ribs that will clip to the center ring. This design is easily manufacturable, and it's easily manufacturable and maintainable. The third one was creating a sort of parabolic spheroid, which was like we do like cross cutting and of that spheroid, and we just basically 3D printed. The main problem was with this idea was like we had the constraint of the 14 by 10 by 10 cube, and we couldn't print this design. So basically, we selected the second design, which was very simple, efficient, and satisfies all the requirements. So I'm gonna pass it to Carlos, who's gonna explain more the mathematical models we use.
Thank you. So basically, what we have here is a problem that we have a parabola where our ribs will set the edges of the parabola. So basically, what we have is that we have to do the parabola as big as possible to concentrate all the energy that comes from the base station, and then it will bounce to the focal point. So basically, based on math, we can see that we need a rib do that shape. But we have a problem here because we can do something like this because of our constraints. So what we do, we take the rib and divide it in 3 segments, so such that we obtain a larger and efficient way to obtain more energy.
Howdy. So this is our small scale model. We cut it halfway through so you could see this is the mylar film that we would use. This is the film that would project the rays back onto the receiver, and that's what would make this actually work. Beneath that, you have your skeleton, and right in the middle here,
can see that it is a central ring that he was referring to. Now, this central ring will have 12 kind of 12 heads, such as that, and that's how this mill head will clip onto it. Now, if you notice, there's a groove there's a big kind of structure at the top that prevents it from moving too much in this axis.
So the groove he was describing was actually the one you may see in the C shape on the left side of this diagram, and the circular shape there actually fits into the groove there, so that it will hold it and it won't wiggle from side to side, similar to a ball bearing would. And instead, it's going to act like it's going to give it 1 degree of rotational freedom, so that it can, so that these things can move up and down to act like a parabola and sort of fill the shape. So if we could just like raise it up a little bit. Yeah. So you see, like these are all bents and they have little joints in them. So every joint allows us to further approximate having a parabola shape and allow us to get a better amount of signal going towards the center receiver.
Mm-hmm. And this is when we get back to the receiver itself. So the receiver is mounted upon just a normal rod. There's nothing special about that. But if you look closely, there's a thread right here and a thread fitting right in the center of the ring. The reason we did this is because you're always going to have to adjust the height of this receiver to get the best reception. So if you were to turn this clockwise, you could decrease the height of this, and counterclockwise to increase the height of this to get the most effectiveness out of this device.
So the foci is going to change based on how you angle the arms of it. So what he's saying is like you just adjust it up and down to compensate for the different scenarios that you may be in. We have a list of constraints and solutions that we had to follow. So some of the constraints were we needed a good approximation of parabolas, which we tackled by having the different segments in the arms. We wanted max bandwidth, so we allowed the arms to actually, if you printed more of them, you could attach more of them on the outside of the segments, and then you could actually make it bigger and choose the angles that you want to do in order to make it work the best. We did ergonomics for easy assembly, and my friend Fu here is going to help us through the rest of it. Yes.
So in conclusion, we were able to design a highly efficient as well as simplistic design for a parabolic antenna. This antenna has all of the components are interchangeable. So if like a leg breaks, you're able to fix it and repair it instead of having to throw the whole thing away. Furthermore, the only two tools you need to fix or to build it is your two hands. That's all you need. You don't need any hammers, you don't need anything, just your hands. Third, the internal components, the electrical wires, the wirings, they're all internal. So there's no exposure to weathering, which we all know is detrimental to fixtures and to these electrical components. Lastly, we made the receiver be able to adjust. So it adjusts accordingly to the focal point location. So thank you all for listening to us. And if you all have any questions, please let us know.
Yeah, and a final acknowledgement, we'd like to acknowledge the team that puts on Aggies Invent and it lets us happen, and also NASA and all the people that were out here giving us their stories to motivate us to actually build this product. Thank you.
Thank you. We have time for a couple of questions.
Yes, sir.
How good is the parabola with 3 legs? Do you satisfy the requirements of focusing the waves?
Yes. Yes, we consider that. We assume that all the energy is going to concentrate to the plate and go focus on here. But the movement of and we assuming that it's in the focal point, but really, but what happened really is because this could be irregular at some point. We have to we move this such that we we concentrate the position with the maximum energy. So basically, what we have here is like something that you can adjust to do efficiency in terms of energy.
But how can you do the curvature, the smooth curvature with the Milo? You said the other material.
So because these points are segment of the parabola, right? So you see this here. We have the parabola. This laminar is adjust on the points that touch the parabola. So
that's exactly my question. You have only 10, 20 points that are exactly on the parabola. The rest are straight.
They should. If we increase the number of segments, we fit the parabola, right?
Yes.
Yes.
So why not have 4 or 6?
Because of the constraint we have in size. We want to collect as much energy we can. At the same time, we need a lot. We need to we have some constraints in our design, like in the cube. So all the components can be developed inside a cube.
Oh, furthermore, the more segments you put, the less durable it is. You're sacrificing durability. You have to have a right balance. You know? For us, 3 segments is sufficient enough. You know? If you have more, yeah, you may have a better coverage. That's true, but you also have weaker components. So.
And we did consider curved segments because obviously it would make sense to use curved segments for a curved parabola. The only problem with that is curved segments do take up a lot of space, and also their center of gravity is shifted forward, so that's, printing is going to be a little bit of trouble.
Did that answer your question, sir?
Okay, one more question. So what I understand is that you've got adjustability. You're going to construct this thing, and then you're going to start adjusting to make it work.
The theoretical position will be in the focal point, but because it's not as regular. Imagine this. It's made. So have a lot of problems in the construction. So we need to move this to find the best point to collect all the energy. That's our goal.
Your question, Olympic?
Just that.
Okay.
All right, thank you all very much.
To explore the unknown, humankind must continually innovate to create opportunities for growth and development. Growth requires building the amenities we as humans require to survive new and changing environments. Currently, we are limited in this capacity by our inability to build locally in microgravity. The solution is a Tensegrity prism. These prisms allow the 3D printing of lightweight, strong, independent structures that can be combined to construct super stable habitats, robotics, and much more. Our self-stabilizing 3D printable prisms are designed to be easily printed and combined in a low-gravity environment. This allows for a maximum variety of uses from a minimum volume of material. Imagine a world where living in space is not just possible, but easy and enjoyable. Cruising along on Tensegrity-based space colonies. Everything you need for a life in space, possible due to the flexibility and power of the Tensegrity prism.
The Tensegrity, and our project was to create a Tensegrity prism building block for construction in space. My name is Crystal Torres.
I'm Monzo, Garrett Harmon,
Race,
Marcela Cabral.
and Zach McAvoy.
So the problem is that currently we have no way to effectively build and construct in space. We build in Earth and then have to transport to space. So the solution to that, what we've come up with, is a 3D printable unit that can be used to construct whatever structure you would like to do. And this unit is built with the structure of a Tensegrity prism. To tell y'all more about what a Tensegrity prism is and how it works, I'm just
So a Tensegrity prism is basically made of three rods and 9 strings. The 9 strings are in tension that also pulls the bars in compression. And these Tensegrity prisms are building blocks that have 90% less mass than the certainly required to have a certain weight on top of it. So this reduction of mass and its ability to be folded into a simple thing completely makes it a very movable object. And in our case, for the 48 hours we've been here, our main problem was to design to be able to print this same thing in space, and that meant we'd be able to reduce the mass of material that we needed to take to space, and also reduce the cost of space construction. So for the 48 hours we've been here, we looked at research materials. We printed small parts of the model so that we didn't waste time, and we could measure and see if they fit into each other. And we divided our labor according to the expertise of each members. We had a lot of discussions with our mentor, Dr. Bob, who's the inventor of this prism. And we also had a lot of feedback from our astronauts and expertise the whole day. Now I'd like to pass to Garrett, who's going to talk more about our integrated prism.
Thank you so much. So immediately, as soon as we got here, within an hour or two, we were already in our team with our mentor talking about how we're going to do this, because this is a very, very, very unique design that has the potential to have a big impact on building and structures in space. So we knew right off the bat that we wanted to build these, but we needed to 3D print them. So the basis of the structure is that it's under stress, and that stress is what provides the stability. So how do we 3D print something under stress? The answer is you can't do that. So we needed to build the structure inside of the printer and then adjust it afterwards to create that stress, to create that stability. So we began brainstorming, and we came up with 3 initial ideas, the first of which was to pinch these strings. By pinching the strings, you pull the bars together, and that twists it into the stable form. The second idea was to extend the bars, and when you extend them, you make them longer, and you bring the strings closer together in proportion to the size of the bars, thus creating the tension. The last way that we came up with was to twist the strings. By twisting them, you're also decreasing the length of the strings, bringing them into that tension. So we kind of talked a little bit about brainstormed a little bit more, and we summarized it all up into one solution that's a little bit different. It's using a shape memory plastic or polymer. What this polymer does is it's easily 3D printable. We can print it into our device, and then as the device cools, the polymer shrinks. And what we can do is we can print it, and as it cools down, it twists into the shape while remaining flexible, providing the strain and the stress that we need to provide a stable structure. And now to talk a little bit more about the design aspects.
Thank you, Garrett. So we had the opportunity to sit down with Dr. Skelton, and he really talked to us about the prism and how it works. And if you see right here, as Manjula already previously explained, there's 9 members in tension and 3 members in compression. And what we were able to figure out through his calculations is that we can optimize this structure by performing calculations through MATLAB. And the key component for this prism, whenever we did 3D print it, is using a shape memory polymer. The way it would work is that we would heat it up, and then it would expand. We would put it into the desired configuration, once we had that desired configuration, we would let it cool down, and once it would cool, it would shorten, thus giving the prism the tension that we need. So 3 inputs that we took into account when creating the MATLAB program was the maximum force, the modulus, and the bar length. Given those 3 inputs, we have outputs that will give us the length of the strings, the length of the bars, and the radii that we would need for it to be optimally strong and flexible, lightweight for any application that we would possibly need. And the significance of this program, or having a program, is so that would reduce any possible failures, and then making this already more cost effective than it already is. Next, I'm going to pass it over to Marcel that will talk about the obstacles that we encountered.
So the idea that we had about the shape memory polymer did bring a lot of challenges to it. One of them being its availability here. So, but we did get a hold on some flexible wire, which ultimately has the same properties of the polymer that we were planning on using. Now, how do we 3D print with pre-stress? So our idea was to use a polymer, and the 3D printer would actually heat it up and it would stay in shape. But since we don't have the polymer, we used the battery's voltage to create a current, which would later on heat up the wire. Now, the material that we actually used was not as strong as we would like it to be. So when we were constructing the prism, it would actually bend. So hopefully the resources that we do have in space are more stronger, and we are hoping to have like higher resolution printers and stuff like that that would actually help on the building of the prism. And now Sab will provide some details of how we can use this.
So the tensegrity structure has a lot of potential applications now and in the future. Currently, we are using them in bridges. As you can see here, this is a bridge based on the tensegrity structure design. Moving slightly into the future, NASA is building prototype robots based on this design as well. And all the way in the future, even potentially full habitats, providing their own centripetal gravity and entire life support systems based on this design. Our 3D printed tensegrity prism that's self-assembling is going to be the building block of future space construction. Not only does it have a wide variety of uses in a microgravity environment, but also here on Earth for the purposes of deploying infrastructure and shelter and emergency environments. Again, we want to thank everyone here at the EIC, and especially Dr. Bob Skelton for all the time that he spent with us, especially on that first day. Thanks. Thank you.
It's time for a couple of questions.
Yes. Can you explain the self-assembly? I didn't understand.
So we weren't able to fully incorporate it because of the structural problems that Marcelo talked about, but essentially we would be using the shape memory polymer in place of some of these strings. And along with the heat in the print bed, we would be able to print it in an unstressed state, almost flat. And then when removed from the heat of the print bed, they would tense up and automatically provide this design with no further assembly directly out of the 3D printer. We used the wire in this case to demonstrate that ability, but when we had structural designs, we weren't able to fully incorporate that wire to take the place of some of these yellow rubber bands.
Anyone else? Did you give any thought into how you would put multiple of these together? Because that's your whole purpose, is to put more than one.
Sure. It's actually sort of the main way that these would be used. They essentially function as fractals, and you can continue to replace not only putting them next to each other, but replace any of these members with the tensegrity prism itself. But they essentially function by simply placing them next to each other. And when you have ones that are more geometrically perfect than this, there's a point at the bottom and the top where these joints touch these wires. So they function as a group, but they don't put stress on any individual neighbor.
The pain point here was being able to print your own building blocks in space.
Yes, and to do it in one print with no assembly once it comes out of the printer. So an entire block comes out of the printer ready to go.
Ready to go.
Yes.
Did you look at the current efforts in printing graphene for space construction, or how would this compare to that?
No, that was not really.
That's something that I briefly breezed over.
Yeah.
For our, like, for this structure, for this exact structure, it would change the way that we use the polymer. We wouldn't want to use it for the actual compression bars because at this scale, there was some research done with compression on it, and it didn't work out too well. If anything, we could mix it in with polymer and we could add electric properties to it, and we could put a current through it and stimulate that polymer that way rather than through heat.
Yeah. Thanks, guys.
All right, thanks very much.
The final frontier. This is the future. Long-term missions to Mars and beyond. But even in space, we are human. Our basic needs are still clothing, food, and shelter. While clothing and shelter have been sufficiently supplied, fresh food has not. At Stellarponics, we believe that hydroponics is the key to survival.
Today, the majority of astronaut food is dehydrated and prepackaged. They have a mere 65 varieties of food, many of which lose their nutritional value in just a few years' time. Current NASA food production systems are not able to be expanded to support long-term sustainability. In addition, these systems require non-renewable supplies, such as plastic and soil, which have to be shuttled to and from Earth. Introducing the HydroHex by Stellarponics. It's fully modular, printable in space, and utilizes pre-existing water and light sources. It supports the growth of a variety of fruits and vegetables, ranging from leafy greens, such as spinach and lettuce, to root-based plants, like potatoes, radishes, and peanuts. That means our astronauts can enjoy a well-balanced diet, rich in minerals, carbohydrates, and proteins.
Stellarponics. Today's seed, tomorrow's sustenance.
Howdy.
Howdy.
My name is JC Park.
My name is Ray Villarreal.
I'm Joseph Valencia.
Kate Paps.
Sneha Chawla.
Wes Keene. And we are Stellarponics. We had the pleasure of working with our mentor, Dr. George James, and Ray is going to start us off with our needs statement and challenge.
Okay, so basically in our needs statement, one of the biggest things was that currently just to keep 6 astronauts in space for 1 year costs $90 million. Just on the space shuttles of sending food backwards and forwards. That's the status quo and it does not work. So our needs statement was basically supposed to be something reusable, sustainable, a plant containment system that could be printed as you needed it. So we ended up going with hydroponics because overall they create healthier plants. Right here we have a diagram of a plant grown hydroponically. It has really small roots, isn't resource heavy, but it has a lot of sustenance for the astronauts to eat. Currently they have soil which have big roots, really really resource heavy, and not much food for the astronauts. So really we just want to have fresh, nutritious food for them. If you look at that picture on the top right, you see their current food. They only have 65 varieties of food, over 50 of which lose the nutritional value in just a year's time. Go ahead and cross that out. We don't want them to be eating that food. We want them to be eating nice, healthy salads that are keeping them nice and healthy. So we make sure to have an expandable design so they can go any type of food.
Alrighty, in regards to the design, our end goal was to be sure that we could grow the maximum food per unit volume, but also make sure that the structure we used delivered all the resources that the plants needed to grow, space, the water, and the light. So we brainstormed a number of ideas, the first of which was a rectangular prism, and we would grow the plants out of every single face of the prism throughout the entire length of the prism. And then we had also decided to try some cups and just growing the plants out of these cylindrical cups. We also tried what we call a triangular tree, which you can see in the top left corner of the demonstration. That was very efficient, but didn't quite give us everything we needed. We ended up settling on a hexagon design. Furthermore, that was just a piece of the design. We had other factors that we needed to consider, like whether or not we wanted to use soil or aeroponics, but we ended up deciding on hydroponics. And in all of these different features that you see, the bold word is what the feature we ended up choosing underneath all of the different categories.
Once we started working on this project, we all realized one of the most important parts of getting this to work is we had to have proper connecting joints. We decided to go with dovetail joints. And as you see on the top left picture, we started out with a full hexagonal structure, and we cut it in half to test the joints. We found out that took way too long to print, and we just wanted to test the joints. So we decided to use less material, print individual legs, and we saved a lot of time on our printing and testing that way. We made several changes to tolerances until we found out the one we wanted to use, and this is probably the most important part of our project, because without it, it's not modular. So we focused a lot of time on this, and we wanted to really emphasize the tight fit to keep the water inside and contained in the structure.
What we ended up deciding and based our decision around was that we wanted a real full modular design. So basically, versatility, so we could change it in different arrays, make the structure in whatever possible way we want, have fluid flow through it with the least number of parts. So if you notice, there's holes on the side for water flow. What you can do is you can either have it, as you can see in the screen, where they're next to each other and make all the way around so the water flows, or you can cap it off, which we make caps. We were considering a cap or some kind of plug or something like that, but we decided not to because we didn't want all these pieces flying around. Make it simple, just easy. The other option you have with this design is that you can actually stack them. So you can grow long plants such as carrots or potatoes inside it and take it apart, clean it, take the plant out, you can reuse it. If it becomes damaged or anything, you can melt it back, just like 3D printing. It's great. So we'll go to the next slide. We'll just pass this.
Judges, you can, remove it. The two are sliding one on top of the other. You could put it in.
Completely slides apart. Completely slides apart. We also did a flow demonstration in SolidWorks, a CFD per se, and I included the documents on your table if you want to check that out. We just picked a random flow rate, but we increased the flow rate at different in different designs to see if the structure would actually flow, and also if it would actually in our structure we had to mess around and see if it would actually seal. And using surface tension, we did that well.
So, as we have seen, we could grow some carrots, but we can also grow leafy greens. We have some celery, some lettuce here, and you can change the diameter of the cap, which is here, to accommodate whatever vegetable you want to grow. But how many of us actually want to eat salads and lettuce every day? I don't think that's many of us. Our astronauts need carbohydrates, proteins, some more fiber, and some really tasty food. With this system, we can grow, like I said, carrots, radish, root-based plants. So stuff that grows inside your system and stuff that grows outside your system. We have groundnuts, we have strawberries. And all of these plants that I have mentioned here have been grown hydroponically on Earth. So there is potential to grow them in space.
So the really neat part about our technology is that it's reusable. That was a huge factor for using it in a microgravity climate where they have a 3D printer. Taking stuff from Earth to the space station or to a different planet, let's say, it's very expensive. So reusing this plastic filament was a really important part. The other thing is that it's not limited to hydroponics or plant systems. That's what the challenge was presenting to us. However, we found that there are several combinations of uses given our hexagon design. You can use them for things like furniture, building structures, storage spaces, make a fanny pack. Really, the space is the limit. So we are, excuse me, we are Stellarponics, today's seed, tomorrow's sustenance. Thank you.
Thank you. Do you have any questions?
Tell me again about the why you decided that this wasn't an elite, given the tolerances of 3D printing the different parts.
I'll take that one. For this shape, we have to make sure we incorporate a system for water to flow through it. So we wanted to focus on a really tight fit with these plates. You don't have to use plates either. You can be more practical. You can use duct tape. What that'll do, because of the water tension and microgravity, it'll be more likely to hold itself in a container. It won't get out of these cracks as easily as it would here on Earth. So that kind of was our thought process. That we don't really know how to test that without actually testing it physically. So for now, we decided to go with plates. There's, in the future, we could figure out a different type of technology, different design that would actually contain it in a better way. But for now, this was the best thing we could come up with.
Also on the plate design and the holes, if it were a problem, we left the design open. If you want to add O-rings or any such thing, you can't physically print that with only ABS, of course. And with our design constraints, that's just the module. But if we wanted to add on to it and enclose it with O-rings or any such, I know other teams are using silicone, which we don't have available right now, but it could be expandable onto. It's just the body and structure. That's what we're keying into.
What was the value of gravity you used in SolidWorks flux press?
I used a really small value, I believe it was 0.0089,
Then did you look at what happens, are carrots in this shape or they are spherical in space when you grow them?
Are you saying in the shape of a hexagon? How it
Yeah,
grows in the shape?
it seems to me you're still,
in
you
space?
think like gardening on the earth. If you grow carrots or lettuce or other objects or other vegetables in microgravity, will they be more spherical perhaps?
I'll take that one. So right now, in space, we just had lettuce that's grown, and that grows more open, but they've not grown anything that is root-based, so we don't know if these are going to grow long. But they do go towards the nutrients, and the leaves will go towards the light source, and a light source would be on top, and the roots tend to grow opposite from the light source. But we do not know if they're going to grow as long.
So how does microgravity, my question actually is, how does microgravity influence your design?
The water flow in the design?
The water flow, but also the growth of the vegetables. So it is a cylinder basically, hexagonal cylinder.
So one of the other features of our design is if we have a hole over here, and we can have another one this side, and we can have plants growing out of both sides. We can have plants, if it's like celery or something, we can have leaves growing out of here. So, small things like herbs that do not need a lot of nutrition, they can grow out of the side. Our bigger plants can grow out of the top, out of the bottom. So this design allows us for modularity as well as growth in every direction, as long as you can get your nutrition right.
Okay, I think that's all the time we have. Thank you very much.
When you feel sick, you might go to your doctor to find out what's wrong. Your doctor likely asks you some questions and probably orders some tests to be done. After analyzing the results of these tests, your doctor might find that you have a nasty virus or another problem. But what if you couldn't visit your doctor directly? In space, Astronauts can't analyze biomedical samples for diagnostic purposes. They can communicate with the doctor, but critical tests and physical contact are lost. This is the problem we're trying to solve. A lab on a chip is a functional solution for these astronauts. These chips analyze bodily fluids to provide data, which can be used to reach medical conclusions. Labs on a chip can be applied to this problem astronauts face, but microgravity in space changes the rules we must play by. Our microfluidic technology takes advantage of the capillary behavior of fluids. This negates the need for an external source of fluid flow. By removing these external energy sources, we can eliminate vital payload weight and cost for transportation. The speed at which bodily fluids can be analyzed is an extremely important capability. Utilizing 3D printing innovations in space makes this capability very affordable. Microfluidic lab chips can be used on the International Space Station and during long-term space missions. Closer to home, this technology can be used in low-resource areas around the world. At Hilsa, we are designing these microfluidic applications for affordable, rapid prototyping. Join us as we fabricate the future.
Howdy!
Howdy.
My name is Uday.
My name is Sagar.
My name is Jaskira.
My name is Mohammed.
My name is Akhil.
My name is Wenjao.
And we're Team Hilsa. Hilsa is Icelandic for health, which is a problem that we are trying to solve here. The project that we were given was to design and fabricate a microfluidic device capable of analyzing a human sample. Microfluidics is using very, very low volumes to process for information. The three main goals of our project was to characterize microfluidic flow and microgravity, to demonstrate additive manufacturing of labs on a chip, and to illustrate a microfluidic mixing chamber in our device. So first, before we could actually design a lab on a chip for space application, we had to think about what we do on Earth right now, because there's a lot of lab on chips being used. So we came up with these ideas where we thought, okay, well, if we could have a lab on a chip and we put a sample and have an astronaut draw liquid through their mouth, that could work. You know, it's easy to do, but we thought that maybe if we are using bodily fluids, it's not such a nice thing to do. So the next thing was using syringe pumps that we use on Earth already. But then that would add to the payload, and it isn't as efficient because you'll be storing samples in the syringes, and that will produce a lot of waste. So then the next step was, why not just use what the nature gave you? That's no pump, that's your body that acts as a pump. There's already a pressure flowing through your blood, and you can use that to pump the liquid inside the chip. So this is our final design that we came up with after going through all those brainstorming sessions. So you see we have a detection platform at the bottom. Right on top of that sits a lab on a chip, which has microfluidic channels. These are hundreds of microns thick and wide. And then it has a finger placement unit where you punch in and it draws a liquid. I'm going to have my colleague pass around some samples and prototypes for you to look at. We also have a display so that we can get the readings and the samples being shown here. So to meet our first goal for this design, we had to see how the fluid flow behaves on Earth and in space. So on Earth, the gravity dominates over the capillary forces, but that changes the game in the space where the capillary forces become dominant, such as you would see on wicking of cotton ball dipped in an oil on Earth, which is shown in the equations and the diagram. Sorry. But because we have talked to a lot of astronauts, and especially the ones who have worked in ISS themselves, and we have also read the simulations from NASA, we know that capillary forces will be dominant effect in the microfluidic chips, and we just put the blood on the chip, it will immediately draw in. So we don't have to worry about any external pumps. The second goal was to actually fabricate. For that, we used 3 different technologies of printing. We used the extrusion printing. We try to use it. You can see that we try to generate some of these devices. Oh, sorry, automatically went through. It was not clear for us to actually be able to see anything to the first device, which was extrusion produced. The second one was polyjet printing, which we tried to use, but we had the material depositing, so we couldn't really get the material to come out. And then the third one was stereolithography, which gave us the best result and what we went with, and we could actually print hundreds of microns resolutions using this 3D printer. The third goal was to actually test the functionality to make sure that this device will work. So first, one thing we wanted to test was mixing chambers, and the reason why this is important is if you see on the image on the right-hand side, the 2 colors represent the 2 liquids that are coming in through the 2 channels, and as they merge,
because the Reynolds number is so low at such small volumes that you need diffusion to play the role in mixing chambers if you don't do anything active. So that's why we increase the surface area by making this S shape that allows for the time to flow and the fluid to mix. And the video is going to demonstrate that, where the red and the blue liquid mix to form a purple liquid right here at the bottom of the channel. So as you see that the purple colored liquid comes out as the two liquids are mixed towards the end of the channel. The next part of functionality testing was actually the detection, because we want to be able to capture something. Because we could not do a biological study in this environment because of the IRB and IBC reasons, so we had to resort to some kind of simulation. So what we did was we tested DI water. We mixed the water with salt. We checked the PBS, which is a buffer containing some ions, and we test the collagen microspheres, which are 200 microns mixed in PBS, and we trap them in the membrane right here. If you see, we were able to fabricate a mesh that was 100 microns porous, and we were able to capture these microparticles, as you can see by the change of the resistance for the collagen particles.
So for cost analysis of our design, we had to take into account how NASA currently works with biological substances. To actually analyze bodily fluids, astronauts have to send back their samples back to Earth so they can be accounted for. And in general, for an ISS to Earth cargo cost is approximately $10,000 per pound of cargo. Prototyping on the International Space Station with our design would be approximately $10 per chip, excluding the cost of the printer because we assume it's already been acquired. But the real important part here is saving time in analysis and diagnosis through the bodily fluids. In normal clinical settings, you have to wait at least 3 to 4 days. 3 to 4 days to get a result from your doctor. With the ISS, you can definitely get it quicker. Further application of our design is obviously healthcare monitoring in deep space. This isn't capable yet. Our design is modular enough to be useful. It's also low cost. It also provides low cost and pre-diagnosis methods in already developed nations. You might have heard of this as personalized healthcare. If you prick your finger and find out that you might need to go to the doctor, you take a lot of the guesswork out of it. In developing areas around the world, we can utilize this technology for quick diagnosis. So you can specify specific illness to search for, and design a chip that can detect certain antibodies or pathogens in the bodily fluid. Further, there are multidisciplinary applications, especially for the ISS. You can do chemical analysis with the specifically designed chip, and biological processes as well. We have a conceptual design that we could use in the future. If we were to partner with a manufacturing firm such as Wiley, we would want to create an all-in-one 3D printer that is capable of printing the microfluidic device, as well as be capable of handling the chemical and biological processes that are required to make these microfluidic devices work for biological processes. In conclusion, we've created a simple to use device. We've also been able to analyze we've also been able to create a device that can analyze biosamples in space. We detected 200 micron microspheres in a solution. And we've also achieved a print resolution of 100 micron through stereolithography print methods. We have special thanks to Rodney Bang, Jim Wilson, the EIC student workers, and the College of Engineering for putting on this incredible event. Thanks, Diego.
Did you actually do a test during the 48 hours to find those microspheres?
We did do several tests. So we we spent most of our time on fabrication because that was a challenge for microfluidics, because a lot of 3D printers are not able to do that. So we started with the polyjet printing because we knew that extrusion is not capable of doing that. But the polyjet kind of disappointed us. So we did go through several iterations of polyjet printing itself. Then we thought, okay, let's scale it up a little bit to try and see better. So we tried to make also the extrusion models, but those didn't work very well either. So then we had access to stereolithography printers that I had read a little bit about, and we knew that those could print better. So we did go ahead and try to print on those printers as well. So we did all of this within 48 hours.
And we were able to capture the microglobules. So we have a solution for PGS, and that contains some microglobules. We had a membrane which was 100 microns wide. These globules are around 200 microns in diameter. So they were trapped before the membrane. We had an ohm meter connected, and as you can see, we could measure the resistance change.
Yes,
sir.
How flexible is your design? If the doctor on, let's say, ISS requires a different test or different volume of the fluid, do you have the flexibility to redesign the same platform, but just make a small change to accommodate that need?
I can answer that. So right now, the design is very generic. It's not designed for a specific test. So the microfluidics in general is very application specific, but that's our goal with the future 3D printer that we want to make, where we want to incorporate the biological and chemical processing, whether that's surface modification, antibodies, proteins, anything that would attach to pathogens and viruses within our 3D printer. So at that point, you would have everything in your stock as a raw material, and you would say, I need to detect diabetes, or I need to detect cold, or I need to detect Ebola. I don't know if there's Ebola in space, but you name it, we want to have it. So,
one more question.
So the advantage of your system would be that you could tailor the medicine and chip, because a lot of people are working for detectors on a chip, right? But your system would allow you to tailor it for something that you don't know you're going to need until you're already in space.
Even in the confines of microgravity, where capillary action will be the reigning force in allowing the movement, because we don't want to use an external actuator for payload reasons, and also because you have to be very, very delicate in inserting the fluids through the chip.
And because we are using mechanical capturing mechanisms, you're absolutely right that you can capture anything that's bigger, but for specificity reasons, to be able to differentiate certain pathogens over the others in a sample, we would still want to accommodate for at least some kind of antibodies that will detect only that kind of thing that has been detected on Earth before. So we want to take into account electrical detection methods as well as fluorescence, quantum dots. So this design can be made just adjustable with other biological methods and optical detection.
Okay, thank you very much.
Okay, that brings us to the end of the presentations. Thank you very much. Y'all have done an outstanding job. I think that the judges are going to have a very difficult time. We're going to retire to conference room 1 for just a few minutes so we can talk over what's going on. While we're doing that, if y'all don't mind, kind of help pick up and clean up, and let's get everything organized again. Just kind of get everything cleaned up a little bit, and then we'll be right back and hand out some awards. Thank you very much. Thank you very much. Again, thank you, teams. Y'all had an outstanding set of presentations and made it very difficult for the judges to actually decide who was going to be receiving these awards. The first off, I want to say, and I would like everybody to give a warm appreciation to the real sponsors of this event, and that's been Aerospace Engineering and specifically the Astro Center. So thank you. Let's give a warm round of applause. All right, very, very difficult for everyone. Just 2 quick things. We mailed out an evaluation survey. We want to make this better. So please, please fill out that evaluation survey. And we will also, at the end of this, we're going to take a very quick group shot. So if everybody will come back up here, we'll take a very quick group shot. And finally, at the very end, we want you to help us clean up because classes start tomorrow morning. Bags in here as well, so we got to have this place ready. All right. So for 3rd place, and oh, don't forget. Also, Thursday night we'll have a meeting here at 5 o'clock. I put it in the email to you. For For those of you who are ready to continue, we'll have a meeting here. For third place and winner of $500 is SpaceSip. And Ratika's going to be taking pictures of you. Everybody get in the picture. There you go.
Again.
Wow, Ratika, you've really embraced this. Okay, thank y'all very much. Congratulations. We want the check back, but y'all can take some pictures with it later. All right, and the second place team is Direct to Mars. Precise. Would you please come up here and get a picture as well? All right.
Thank you so much.
And the one that we've been waiting for, the first place team and winner of $1,000 is Stellarponics.
There you go.
Be sure that everybody's in the picture.
We can't take it without Jordan.
Exactly.
There you go.
Okay, you got it? All right. Thank y'all very much. See y'all Thursday. Again, I want to thank everybody for being here. And we will take a very quick group picture. We're going to move some of the chairs and the tables out of the way. Thank you, everyone, for being here. Thank you for an amazing weekend. We'll be posting some more things online. Don't forget about the next Aggies Invent coming up. It is going to be on developing countries, so it should be a very interesting one. Continue to apply and continue to work with us. Thank you very much for the whole thing. Y'all come up here very quickly for a group shot, and then we're gone.
Before we do that too, big thank you for Rodney and his team and for Jim for making all this possible for all of us.
Come on, let's do these tables all the way. Come on, let's go. Everybody's tired.